chapter Chemical Bonding. Let us look at the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to explain why atoms react, explain Clausius-Lewis approach to chemical bonding, define the octet rule, explain the formation of bonds, explain the formation of ionic bond and covalent bond, describe the valence shell electron pair repulsion theory, illustrate the valency bond theory, discuss the properties of ionic and covalent compounds. Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to learn more. In lower classes, we learned that an atom is the basic unit of matter. It consists of a dense nucleus surrounded by a cloud of negatively charged particles called electrons. These electrons are distributed in different orbitals like s orbital, p orbital, d orbital, and f orbital. The distribution of electrons in different orbits of an atom is known as electron configuration. In lower classes, we also learned about the types of chemical reactions. A group of atoms is called a molecule. In the formation of molecules, is there any force of attraction existing between atoms? Moreover, why do some elements exist as molecules and others exist as independent atoms? Let us try to answer these questions and learn more. Let us start our session with the formation of bonds. Earlier, most of the scientists believed that the electrostatic forces are the cause of attraction among the atoms in a molecule. When two atoms come close to each other, the electrons of each atom get attracted towards the nucleus of the other atom. However, the negatively charged electrons repel from each other, and also the positively charged nuclei repel from each other. If repulsion force is less than the attraction force, the atoms combine. The repulsion force is more than the attraction force, then the atoms do not combine. In this way, the formation of bond takes place based on the strength of attraction or repulsion between the constituents of the two interacting atoms. Moreover, when two atoms come closer together, the electrons in the outermost shells in both the atoms get affected. The nucleus and the electrons in the inner shell remain of the atoms that are unaffected by the electrostatic forces. The electrons in outermost shells are called valence electrons, and their shells are known as the valence shells. Valence electrons are responsible for the formation of bond between two interacting atoms. After learning about the formation of chemical bonds, now let us learn about their representation through the concept of Lewis dot structures. Lewis dot structures. Now, the valence electrons of two interacting atoms play an important role in the formation of chemical bonding. Apart from their numerical representation, the valence electrons of an atom can be graphically represented in a short form called the Lewis symbol or the electron dot structure. Learning to represent the valence electrons of the noble gas elements help us in understanding the formation of chemical bonding in other elements seeking stability like the noble gases. The electronic configurations of the elements of the 18th group are shown on screen. Except the element helium, all other elements of this group have 8 valence electrons. Here, the constituents of the atom, the nucleus, and inner shell electrons are represented by the symbol of the element, and the valence electrons are represented by dots or cross marks. The Lewis dot structures of the atoms of noble gases are shown on the screen. Let us do an activity to represent the valence electrons of atoms of different elements using Lewis dot structure. Davy's experiment. Humphrey Davy, 1778 to 1819, a professor of chemistry at the Royal Institution in London, constructed a battery of over 250 metallic plates. In 1807, using electricity from this battery, he was able to extract highly reactive metals like potassium and sodium by electrolysis of fused salts. It was seen that the metal part of the compound migrated towards the negative electrode and the non-metal towards the positive electrode. So it was proposed that metals are positively charged and non-metals are negatively charged, and they are held together by electrostatic forces in a compound. While this explanation could explain bonding in sodium chloride, potassium chloride, etc., it could not explain bonding in carbon compounds or diatomic molecules of elements. Let us learn about the scientific theory on chemical bonding based on valence electrons. It is called the electronic theory of valence, proposed by Lewis and Kozel. A satisfactory explanation on the formation of chemical bonds between atoms in terms of their valence electrons was given independently by Lewis and Kozel in 1916. Their logical explanation on the role of valence electrons in bond formation was based on the lack of chemical activity of noble gases. The explanation leads to the proposal of the octet rule. Now, let us learn about the octet rule in detail. We know that in any chemical reactions, the reacting elements must get octet configuration, that is NS2 and P6, in the outermost shells at the end of the reaction. The 8 electrons in the outer shell give stability to the ion or atom. Based on this observation, a statement known as the octet rule was framed. Perform the following in a way that the outer shells of the elements from group 1A to 8A attain octet configuration. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Enter the appropriate symbol of the operation and required number of electrons. Knowledge check. Now, let us learn the significance of octet configuration in the formation of chemical bonds. Chemical bond. In order to explain the formation of chemical bond in terms of octet configuration, Lewis described an atom as a positively charged kernel with the valency shell containing a maximum of 8 electrons. The kernel included the nucleus and all the electrons in different orbits of the atom except the valence shells. Element, except the noble gases, seek to have 8 electrons in their valence shell. For this purpose, they form bonds with atoms of their own element or other elements. In this way, chemical elements become active in nature. Make a note. Noble gases are passive in nature due to their high stability and inertness. Definition. The force of attraction between any two atoms or a group of atoms that results in the formation of a stable entity is called a chemical bond. There are many types of chemical bonds. The most important types of chemical bonds are the ionic bond and covalent bond. Let us learn about each of the chemical bonds in detail, beginning with the ionic bond. Ionic bond. The following facts were used by Kozel to propose the formation of an ionic bond. Two atoms of different elements in the periodic table form an ionic bond when transfer of electrons takes place from one atom to the other atom. Group 1A elements are present on the left side of periodic table, and these elements are highly reactive metals like alkali metals. Similarly, Group 7A elements present on the right side of the periodic table, and these elements are highly reactive non-metals like halogens. Noble gases, by their very nature, contain octet configuration in the outer shells of their atoms, except helium. That is why these elements are chemically inactive and stable. To obtain octet configuration in the valence shell, like to noble gases, metal atoms that have 1, 2, or 3 electrons in the valence shells normally lose those electrons and form stable positive ions called cations. Note: the number of electrons lost from a metal atom is the valence of its element, which is equal to its group number. Example: sodium and magnesium have valence 1 and 2 respectively. To obtain octet configuration in the valence shell, like to noble gases, non-metal atoms that have 5, 6, or 7 electrons in the valence shells normally gain 3, 2, or 1 electron and form stable negative ions called anions. Note: the number of electrons gained by a non-metal element for its atom is its valency, which is equal to its group number. For example, the valency of chlorine is equal to 1. A cation is a positively charged ion formed when 1 or more electrons are transferred from an atom. An anion is a negatively charged ion formed when 1 or more electrons are transferred to an atom. Let us learn about the formation of ionic bond. Ionic bonds are formed when positive ions and negative ions come closer due to the electrostatic force of attraction between them. It is also known as the electrostatic bond. Since the formation of this bond between two elements involves transfer of valence electrons, it is also called the electrovalent bond. Definition: the electrostatic attractive force that keeps cation and anion together to form a new electrically neutral entity is called ionic bond. Let us learn about the formation of cations and anions in the compounds sodium chloride, magnesium chloride, sodium oxide, and aluminium fluoride. Let us learn about the formation of ionic bond, NaCl. sodium chloride, MgCl2, magnesium chloride, Na2O, sodium oxide, AlCl3, aluminum chloride. Click each tab to know the formation of ionic bond. Formation of ionic bond in the compound. Sodium chloride. The formation of ionic bond in sodium chloride is shown on screen. One sodium atom transfers one electron to the chlorine atom and forms Na positive and Cl negative ions. These ions get attracted towards each other and form the sodium chloride compound. Cation formation. Sodium with atomic number 11 loses one electron. It becomes a cation and to attain the stable configuration of neon. Anion formation. Here chlorine gains the electron transferred to it by sodium and attains the configuration of argon. It is the anion in this bond. Magnesium chloride. The formation of ionic bond in magnesium chloride is shown on screen. One magnesium atom transfers two electrons, one each to two chlorine atoms, and magnesium becomes Mg2 positive. Two chlorine atoms gain the electrons transferred to them by magnesium ion. Finally, magnesium chloride is formed by the two chlorine ions and magnesium ion. Cation formation. Magnesium with atomic number 12 loses two electrons to attain the stable configuration of neon. It is the cation here. Anion formation. Two chlorine atoms gain the electrons transferred to them by magnesium ion and attain the configuration of argon. They are the anions here. Sodium oxide. The formation of ionic bond in sodium oxide is shown on screen. Two sodium atoms transfer one electron each to one oxygen atom to form two Na plus and O2 minus ions. These ions, 2 Na plus and O2 minus, attract to form Na2O. Cation formation. Sodium with atomic number 11 loses one electron to attain the stable configuration of neon. Two Na atoms lose one electron each and become cation. Anion formation. Here, oxygen gains the electrons transferred to it by each sodium atom and attain the configuration of neon. It is the anion here. Aluminum chloride. The formation of ionic bond in aluminum chloride is shown on screen. Each aluminum atom loses 3 electrons and 3 chlorine atoms gain them 1 electron each. The compound aluminum chloride is formed when its component ions by the electrostatic forces of attractions. After learning about the formation of cations and anions, let us now know about the arrangement of ions in ionic compounds. Cation formation. Aluminium with atomic number 13 loses 3 electrons to attain the stable configuration of neon. It is the cation here. Anion formation. Here, chlorine gains the electron transferred to it by each aluminum atom and attains the configuration of argon. It is the anion here. Arrangement of ions in ionic compounds. Let us consider the arrangement of ions in an ionic compound like sodium chloride. Ionic compounds are made up of a three-dimensional crystal lattice with positive ions surrounded by negative ions and vice versa. The crystal structure of sodium chloride is shown on screen. From the image, sodium chloride is said to possess face-centered cubic lattice crystal structure. Here, each sodium ion is surrounded by 6 chlorine ion and each chlorine ion is surrounded by 6 sodium ions. and sodium ion and chloride ion have coordination number 6. The number of ions or atoms that immediately surround an atom or ion is called the coordination number. Factors affecting the formation of cation and anion. In an ionic bond formation, atoms either lose or gain electrons to get an octet configuration in the outer shell. Metallic elements have the tendency of losing electron to attain the octet configuration in their outer shell. This property is known as metallic character or electropositivity. Cations will be formed by elements with electropositive character. In the same way, non-metals get octet configuration like inert gases by gaining electron. This property is known as electronegativity. Anions will be formed by elements with electronegative character. An ionic bond is formed between atoms of elements with electronegativity, difference equal to or greater than 1.9. The tendency of gaining electrons to form anions or losing electrons to form cations depends on the following factors. They are atomic size, ionization potential, electron affinity, electronegativity. Cations will be formed by the elements of atom with high atomic size, low ionization energy, and low electron affinity. Anions will be formed by the elements of atom with small atomic size, high ionization energy, and high electron affinity. Another mechanism of formation of chemical bond involves sharing of valence electrons between the two elements for attaining octet configuration. It is technically called covalent bond. Knowledge check. Let us learn about the formation of covalent bond in detail. Covalent bond. Jean Louis, 1916, proposed that the atoms could attain octet configuration in their outer shell by sharing their valence electrons with one or more atoms. This type of chemical bonding is called the covalent bond and involves equal contributions from the shared valence electrons. Consider two fluorine atoms which form a stable molecule. Both of these atoms originally contain one unpaired electron in their valence shell. Here, an electron pair is formed between the two atoms by sharing of the electron in the outer shell of each of the fluorine atom. In this way, each atom in the fluorine molecule has an octet configuration. The dots around fluorine atoms represent the valence electrons of respective atoms. Covalent bond. Let us learn about the formation of covalent bond by the elements oxygen, nitrogen, methane, ammonia, and water molecule. Click each tab to know the formation of covalent bond. Oxygen molecule. The arrangement of electrons in oxygen atom is 2, 6. The atom has 6 valence electrons in its outer shell. Each oxygen atom requires 2 more electrons to attain octet configuration in its outer shell. That is why 2 oxygen atoms come closer and share their valence electrons to form covalent bonds between them. The image on the screen shows that both the oxygen atoms have octet configuration in their valence shell by the formation of double bond. A double bond is formed between the 2 atoms by sharing of their 2 valence electron pairs. Nitrogen molecule. The arrangement of electrons in nitrogen atom is 2, 5. The atom has 5 valence electrons in its outer shell. Each nitrogen atom requires 3 more electrons to attain octet configuration in its outer shell. As a result, 3 covalent bonds are formed between the 2 nitrogen atoms by sharing the valence electrons. The image on the screen shows that both the nitrogen atoms have octet configuration in their valence shell by formation of triple bond. A triple bond is formed between the two atoms by sharing of their 3 electron pairs. Methane molecule. A methane molecule, CH4, is formed by 1 carbon and 4 hydrogen atoms. The arrangement of electrons in carbon atom is 2, 4. So carbon has 4 electrons in its valence shell. It requires 4 more electrons to complete its octet configuration. Each hydrogen atom has only 1 electron in its outer shell. In order to completely fill its outer shell, a hydrogen atom requires 1 more electron. That is why 1 carbon atom shares its 4 outermost electrons with 4 electrons of 4 hydrogen atoms. As a result, 4 covalent bonds are formed between the carbon atom and 4 hydrogen atoms due to the sharing of the valence electrons of interacting atoms. Ammonia molecule. Ammonia molecule NH3 has 1 nitrogen atom and 3 hydrogen atoms. The electronic arrangement of a nitrogen atom is 2, 5 and that of a hydrogen atom is 1. To achieve octet configuration in their outer shell, the nitrogen atom needs to share 3 pairs of electrons with 3 hydrogen atoms. In this way, the nitrogen atom gets octet electronic configuration with the help of the hydrogen atoms. Finally, 3 covalent bonds formed between the nitrogen atom and the hydrogen atoms. Water molecule. A water molecule, H2O, is formed by 2 hydrogen atoms and 1 oxygen atom. The electronic arrangement of electrons in an oxygen atom is 2, 6 and that of a hydrogen atom is 1. To achieve octet configuration in their outer shell, the oxygen atom shares 2 electrons with 2 hydrogen atoms. The hydrogen atoms get duplet electrons arrangement after sharing their electrons with the oxygen atom. Finally, 2 covalent bonds are formed between the oxygen atom and the hydrogen atoms. Bond lengths and bond energies of covalent bond. Equilibrium distances between centers of bonded atoms which are connected by a covalent bond are called bond lengths or bond distances. It is generally expressed in nm, nanometer or angstrom units. Bond energy is the energy required to break a covalent bond between 2 atoms of a compound to make the corresponding atoms in the gas phase. This bond energy is also called as bond dissociation energy. The table on screen shows the bond lengths and bond energies of different covalent bonds. From the table, we observe that bond lengths and bond energies change from bond to another. The angle between 2 bond lengths of the constituent atoms in a molecule is called bond angle. The valence electron theory could not explain the concept of bond angles in molecules. The theory could not explain why angle in a beryllium chloride is 180 degrees. Angle in boron trifluoride is 120 degrees. Angle in methane is 109 degrees 28 minutes. Angle in ammonia is 107 degrees 182 minutes. And angle in water is 104 degrees 312 minutes, etc. It is explained by the valence shell electron pair repulsion theory. An angstrom is a non-SI unit of length equal to 10 to the power minus 10 meters or 0.1 nanometers or 100 picometers. 1 nanometer is equal to 10 to the power minus 9 meters. Knowledge check. Valence shell electron pair repulsion theory. In 1940, Sidgwick and Powell proposed a theory based on the repulsions between the electron pairs, known as valence shell electron pair repulsion theory, VSEPRT. Valence shell electron pair repulsion theory. In 1940, Sidgwick and Powell proposed a theory based on the repulsions between the electron pairs, known as valence shell electron pair repulsion theory, VSEPRT. This theory was improved by Gillespie and Nyholm in 1957. That is why this theory is also called as Gillespie-Nyholm theory. Basic assumptions of this theory are the valence electrons in a covalent bond between constituent atoms and the valence electrons existing as lone pairs from charged clouds. The force of repulsion between such charged clouds provides specific shape to a molecule. Knowledge of the total number of valence electrons of the charged clouds helps us in predicting the arrangement of those pairs around the nucleus of the central atom and the shape of the molecule. In the formation of a molecule, the charged cloud formed by the lone pairs of valence electrons occupy more space around the central atom than charged cloud formed by bond pairs. A lone pair of electrons means an unshared electron pair or non-bonding electron pair attracted to only one nucleus, whereas the bond pairs are shared by two nuclei. In this way, the presence of lone pairs of the valence electrons on the central atom causes slight distortion of the bond angles from the expected regular shape due to the force of repulsion between them. The angle between lone pair and bond pair at the central atom increases due to excess the force of repulsion between the atoms. This can decrease the actual bond angles between them. If the two bond pairs are present in two covalent bonds around the nucleus of the central atom in the valence shell, the force of repulsion between them will be minimum when they are separated by 180 degrees. This makes the shape of the molecule linear. In beryllium chloride and boron trifluoride, the central atoms, beryllium and boron, did not possess 8 electrons around them in the valence. They have only 4 and 6 electrons respectively. These molecules are known as electron deficiency molecules. If 3 bond pairs are there in 3 covalent bonds around the nucleus of the central atom, the repulsion force will be minimum when they get separated by 120 degrees along 3 corners of a triangle. This provides a trigonal planar shape to the molecule. If there are 4 bond pairs in the valence of the central atom, the 4 bond pairs will orient along the 4 corners of a tetrahedron 3-dimensional arrangement, and the bond angle expected is angle in methane is 109 degrees 28 minutes. If there are 3 bond pairs and 1 lone pair, that is 1 unshared electron pair, then the lone pair occupies more space around the nucleus of the central atom, and the remaining 3 bond pairs come relatively closer as in ammonia molecule's case. If there are 2 bond pairs and 2 lone pairs of electrons around the nucleus of the central atom in its valence shell, the repulsion force between lone pair is greater than the force of repulsion between the lone pair, bond pair. This leads to a decrease in the angle between bond pairs. Drawbacks of this theory. This theory fails to explain the strengths of the bonds. It is because the theory uses the Lewis concept of covalent bond formation. It could not further explain the electronic nature of covalent bonds. Valence bond theory. A quantum mechanical model was proposed by Hitler and London to describe the formation of covalent bond. It is known as valence bond theory. Linus Pauling improved this theory by introducing the concept of hybridization. Valence bond theory. Valence bond theory is explained as follows. A covalent bond is formed between the two atoms by the overlap of half-filled valence atomic orbitals of each atom containing one unpaired electron. Each such unpaired electron has opposite signs. That is why in the overlapping orbitals, the paired electrons are attracted to the nuclei of two atoms. A stronger bond will be formed by the greater extent of overlapping between the two atoms. This gives a directional character to the covalent bond when other orbitals except s orbitals are involved. In the formation of a covalent bond, the electron pair is shared in the overlapping orbitals by the atoms involved in the bonding. Based on the pattern of overlapping, two types of covalent bonds take place. The covalent bond formed due to end-end overlapping of atomic orbital along the internucleus axis is called sigma bond. It is a stronger bond because the electrons are strongly attracted by the nuclei of bonding atoms. The covalent bond formed by sidewise overlapping of atomic orbitals is called pi bond. It is a relatively weaker bond because the electrons are weakly attracted by the nuclei of bonding atoms. Let us learn about the valence bond theory using the examples of the formation of chlorine, nitrogen, and oxygen molecules. Click each tab to know more. Formation of chlorine molecule. In the ground state, the electronic configuration of chlorine atom is shown on screen. Here, the chlorine atom contains an unpaired electron in the 3pz orbital. In the formation of a chlorine molecule, two chlorine atoms with their unpaired electron overlaps with each other. These two half-filled 3pz atomic orbitals of each chlorine atom have opposite signs and overlap in end-end manner along their internuclear axis. As a result, a sigma bond is formed between the two 3pz orbitals of each chlorine atom. Formation of nitrogen molecule. In ground state, the electronic configuration of nitrogen atom is shown on screen. Here, each nitrogen atom contains an unpaired electron in the 2px, 2py, and 2pz orbitals. In the formation of an N2 molecule, two nitrogen atoms overlap with each other. A sigma px bond is formed between two nitrogen atoms due to the end-end overlapping of half-filled 2px atomic orbitals along the internuclear axis. The remaining half-filled 2py and 2pz atomic orbitals of each nitrogen atom form pi bond, py bond, and pz bond by the sidewise overlapping between them. Hence, N2 molecule has triple bond, 1 sigma and 2 pi bonds between two nitrogen atoms. Formation of oxygen molecule. The electronic configuration of an oxygen atom in its ground state is shown on screen. Here, oxygen atom containing an unpaired electron in the 2py and 2pz orbitals. In the formation of an O2 molecule, two oxygen atoms with unpaired electrons overlap with each other. A sigma py py bond is formed between two oxygen atoms. Due to the end-to-end overlapping of half-filled 2py atomic orbitals along the internuclear axis, the remaining half-filled 2pz atomic orbitals of each oxygen atom valence bond theory bond hybridization pz in order to explain the structures overlapping bond angles of molecules. Hence, O2 molecule has modified the valence bond theory and using hybridization concept two oxygen atoms. Definition: the redistribution of orbitals of almost equal energy in individual atoms to give equal number of new orbitals of equivalent energy is called hybridization. Let us learn about the valence bond theory using hybridization concept in the formation of beryllium chloride, BeCl2, beryllium chloride, Bf3, boron trifluoride, NH3, ammonia, and H2O water molecules. Click each tab to learn more. Formation of beryllium chloride molecule. In the ground state, electronic configurations of beryllium atom and chlorine atom are shown on screen. From the ground state, an electron from S block of the beryllium atom gets excited and enters into the p subshell, that is 2px1. As a result, the electronic configuration of beryllium atom in the excited state is as shown on screen. Here, beryllium atom has one electron in s orbital and one unpaired electron in px orbital. Hence, these orbitals are called hybrid orbitals. In the excited state, the beryllium atom undergoes sp hybridization by mixing a 2s and one 2p orbitals. On hybridization of 1s and 1p orbitals, we get two hybridized orbitals at an angle 180 degrees. If the beryllium atom forms bonds using these orbitals, the molecule might be angular. During the formation of beryllium chloride molecule, the beryllium atom contributes two electrons from its outer shell to form two bond pairs with chlorine atom. Here, two sigma bonds will be formed by overlapping of the sp hybrid orbitals of beryllium atom with 3pz orbital of two chlorine atoms respectively. The two sp orbitals of beryllium atom get separated by 180 degrees. That is why the molecule beryllium chloride is linear in shape. Formation of boron trifluoride molecule. In the ground state, the electronic configurations of boron and fluorine atoms are shown on screen. From ground state to excited state, electron of a boron atom form S block enters into the p subshell, that is 2py1. Therefore, the electronic configuration of boron atom in excited state is as shown on screen. Here, boron atom has one unpaired electron in s orbital and two unpaired electrons in p orbital, that is px and py orbitals. In the excited state, the boron atom undergoes sp2 hybridization by mixing of one 2s orbital and two 2p orbitals. Hence, these orbitals are called hybrid orbitals. If the boron atom forms bonds using these orbitals, the molecule might be angular. During the formation of boron trifluoride molecule, the boron atom contributes 3 electrons from its outer shell to form 3 bond pairs with chlorine atom by using its half-filled sp2 hybrid orbitals. Basic assumption: here, 3 sigma bonds will be formed by the overlapping of 3 sp2 hybrid orbitals of boron atom with 2 2pz orbitals of each fluorine atom respectively. The 3 sp2 orbitals of boron atom are separated by 120 degrees, providing trigonal planar shape to the boron trifluoride molecule. Formation of ammonia molecule. In the ground state, electronic configuration of hydrogen atom and nitrogen atom is as shown on screen. This nitrogen atom has 3 unpaired electrons in 2p orbital. Hence 2s and 2px, 2py, 2pz orbitals of nitrogen atom intermix and redistribute into 4 similar sp3 hybridized orbitals. One of the 4 sp3 hybridized orbitals obtains a pair of electrons and the remaining orbitals obtain 1 electron each. During the formation of an H3 molecule, the nitrogen atom contributes 3 electrons from its outer shell to form 3 bond pairs with 3 hydrogen atoms. 3 hydrogen atoms with their valence electron in 1s orbitals overlap with the 3 sp3 hybridized orbitals of nitrogen atom and form similar sigma bonds. In NH3 molecule, there is a lone pair of electrons on nitrogen atom belonging to the fulfilled sp3 hybrid orbital. However, the H-NH bond angle is not equal to normal tetrahedral angle. The angle is 109 degrees 28. Moreover, lone pair repulsion is greater than lone pair bond pair repulsion. That is why the angle between bond pairs further decreases to its 107 degrees 48. Formation of water molecule. In the ground state, electronic configurations of hydrogen atom and oxygen atom are shown on screen. The oxygen atom has 2 unpaired electrons in 2p orbital, that is 2py, 2pz. Here 2s and 2px, 2py, 2pz orbitals of oxygen atom intermix and redistribute into 4 similar sp3 hybridized orbitals. 2 of the 4 sp3 orbitals obtain a pair of electrons and the remaining orbitals obtain 1 electron each. During the formation of water molecule, the oxygen atom contributes 2 electrons from its outer shell to form 2 bond pairs with 2 hydrogen atoms. 2 hydrogen atoms overlap their 1s orbitals with the 2 hybridized orbitals of oxygen atom and they form similar sigma bonds. In water molecule, there are 2 lone pairs on oxygen atom belonging to the fulfilled sp3 hybridized orbitals. However, the bond angle in water molecule is not equal to normal tetrahedral angle. It is 109 degrees 28. Moreover, the lone pair repulsion is greater than lone pair bond pair repulsion, and this further decreases the angle between the bond pairs to 104 degrees 31. Let us now learn about the properties of the compounds formed due to ionic and covalent bonds. The properties of ionic and covalent bond are shown on the screen. From the above table, we understand that ionic compounds like sodium chloride are solids at room temperature. Polar compounds like hydrochloric acid possesses properties like melting point, boiling point, reactivity, solubility, etc. between those of ionic compounds and covalent compounds. In ionic compounds, there exist stronger electrostatic forces of attractions between the oppositely charged ions of these molecules. Therefore, they are solids with high melting points and boiling points. Based on the principle like dissolves in like, they being highly polar, soluble in polar solvents. In chemical reaction of solution of ionic compounds, simply rearrangement of ions take place in the solutions. The reactions are instantaneous or very fast. the forces of attractions among covalent molecules are weak. Therefore, the covalent compounds have low melting points and low boiling points. Based on the principle that like dissolve in like, these covalent compounds are soluble in non-polar solvents because of non-polar nature of solvent molecules. In chemical reactions, related covalent compounds, there exist bond breaking and bond forming. To get products, these reactions are moderate or very slow. Read the questions and attempt the answers on your own. You can click answer for your reference. Drawing skills. The drawing section helps you to sketch images in a step-by-step manner. Click each tab to know more. Drawing skills. The drawing section helps you to sketch images in a step-by-step manner. Click each tab to know more. Follow-up work. Collect the information about the properties and uses of covalent bonds and prepare a report. Draw simple diagrams to show how electrons are arranged in the following covalent molecules. A. Calcium oxide. You have successfully completed the chapter Chemical Bonding.